All right, hi everyone. Welcome to another night of a review session. Thanks for stopping in. Um, so this hour will just really be for y'all to ask your questions. Before the exam, I want to just get any of those last minute jitters out of the way or just last minute clarifications. Um, and just as a reminder, right, your exam is tomorrow. You're going to take it in class. It's all multiple choice. I think it's about 16 questions, and you just take it during class time. So it'll be 10:20 to 11:10. Are there any questions for me about the exam, or do you just want to jump into content? You can use the chat or just take yourself off of mute. Either one is fine. Okay,
Can
so
you
someone,
go over question 11 on the test review?
absolutely.
I just don't understand, I mean, I know why A is the answer, but I was just wondering, what D is, how to interpret it.
Yep. Okay, so that's a great question. So let me get rid of all of this. Okay, so when we're looking at question 11, we're looking at the chemical reaction and we're looking at, right, the graphs associated with that as well. So we're given the delta H and delta S, so the enthalpy and entropy for this. And then, right, we want to select the correct plot of delta G. So what essentially this question is asking is, when is this reaction spontaneous and what graph shows when it's spontaneous, if it's spontaneous at all. So the first thing you want to do is utilize your delta G equation. So delta G is equal to delta H minus T delta S. And we're going to use our delta H and delta S's provided to find what delta H is and then what delta S is. And that's just your products minus your reactants times the sum or times the coefficient in front of them. So for delta S, we have 2 times PCl, which is negative 319.6, and plus oxygen, which is in its elemental state, so that's 0, minus 2 times negative 597. So delta H naught is equal to 554.8. This is kilojoules per mole. Carolyn, yes, I will be posting this afterwards. And then, right, so we have delta H is equal to 554.8. Right, so that's telling us that this has the potential to not be spontaneous, right? The world prefers exothermic reactions. This is an endothermic reaction. So if the entropy is decreasing, then it's never going to be spontaneous. But we do see that if we predict delta S based off of our equation, we're going from a liquid to a liquid and a gas. And so since we're producing gas, our prediction is that delta S should increase. So there should be a time when this reaction is spontaneous. So if we look at delta S naught, then we're going to say we can do the same thing for products minus reactants. So it's 2 times 217 and 205 minus 2 times 222. So delta S naught is equal to 195. And this is joules per mole. Okay. So now that we've found delta H and delta S, before we even predict or look at the graphs, what can we say about when this reaction will be spontaneous? right? If we go back to our delta G equation, delta G naught is equal to delta H minus T delta S. We are plugging in a positive value and a positive value for delta S. So when will this reaction be spontaneous?
Would it be spontaneous when delta G is less than 0?
Yep, it's going to be spontaneous when delta G is less than 0. So what does that mean in terms of temperature? Is it going to be always spontaneous, never spontaneous, high temp, low temp?
High temperatures?
Yeah, right. It's going to be spontaneous at high temperatures because at high temperatures, that delta S and that T are going to be bigger than the positive of delta H. So delta G equals negative at high temps. Okay, so before we even solve for what the delta or for what the temperature is when it becomes spontaneous, we can look at our graphs. If we look at B, right, we'll start with B. We have an axis that is positive for temperature, which makes sense, right? Temperature should always be positive. And then we have a delta G where it's also always positive. What would this be if delta G is always positive? Right? If delta G is always positive, is that ever spontaneous?
No.
Nope, it's never spontaneous. So we know that at high temperatures, our delta G is negative. So this is going to be removed because it has to be spontaneous at some point. When we look at D, right, this is positive temperature, but this time delta G is always negative. Is our delta G always going to be negative in our case?
Nope.
Nope, so we can also get rid of D there. Then that leaves us A and C. So we want delta G to be negative at high temperatures. Which one shows a delta G at a negative? Or which one shows a delta G negative when it's at high temps?
The first one?
The first one, right? Here, we're in the negative range at the higher end of your axis. On C, it's saying that as you increase temperature, we're getting more positive for delta G. So that's not what's happening in our case. We get more negative with higher temperatures. So A is going to be your answer choice here. If you wanted to solve for your temperature and then like therefore your slope, then you could do T is equal to delta H divided by delta S, and you can solve for temperature there. And then the other thing I can say about this is that delta G is equal to delta H minus T delta S. That is kind of close to Y is equal to MX plus B. But we would rearrange it to delta G naught is equal to negative T delta S plus delta H. I guess, yeah, that'll work. That'll be fine. It's technically negative delta S T because X is temperature and delta S is your slope. Okay, does that help there? Ariana, for your question, how do we know that the equation is delta S and delta H? What equation? For the temperature? So we are going to use, we know that it's for the graph because we can take delta G is equal to delta H minus T delta S and rearrange it into the Y equals MX plus B form. So all of these are showing delta G is equal to negative delta ST plus delta H. It's just rearranged from that original form. And that's the slope of the line that's showing it. The equation gives you a straight line plot, so that's what they're graphing here. Yeah, of course. Okay, any other questions on 11? So then you could also prove to yourself, right, that this portion here, where it crosses that 0 point, if you solve for that temperature, it should be about 2,850 for your Kelvin. And that's a good way to check it, right? You didn't solve for the temperature before you picked your answer, so you can check your temperature and see if that matches what you saw. Okay.
Is there a way to work backwards with the temperatures?
Oh, yeah, 100%. So, right, this multiple choice question, you can take the graph that's given to you. If you solve for delta H and delta S, you could always plug in a temperature into X, right? Because that's your X on your X-axis here, and see if you get 0 for delta G, or if you pick a really high number, right, plug in a really high temperature and see if you get a negative for delta G. That's just proving that your line is in the correct spot on your graph.
Thank you.
Yep. Any other questions there? Okay, someone asked for 6, so I'll go and do that real quick, and then we'll do 2. Okay, so for question 6, we have diethyl ether has a vapor pressure of 400 torr at 18 degrees Celsius. And when a sample of benzoic acid, a non-volatile non-electrolyte, is dissolved in ether, the vapor pressure of the solution is 342 torr, and we want to know the mole fraction of the benzoic acid. So the thing to note here is that you have diethyl ether, oops. This here is your solvent, and benzoic acid is your solute. When they say non-volatile, non-electrolyte, this is a Van Hoff factor of 1. So it's not contributing, right? It's just contributing the 1 mole that it has to it. So the other thing that we need to know for this equation, or for this question, is that P of the solution, or the pressure of the solution, is equal to the mole fraction of the solvent times the pressure of the pure solvent. And this is telling you that your vapor pressure of the solution will always be less than the vapor pressure of your pure solvent, right? You have things competing now in the solution, and so it's not always going to be that solvent that's escaping into the gaseous phase or coming back down into the liquid phase, right? You have other particles competing to do that as well. So here we're given 400 torr, and this is the pressure of the pure solvent. And then we're given 342 torr, and this is the pressure of the solution. So we can plug that into our equation. We get 342 is equal to X times 400. And we get the mole fraction of the solvent equal to 0.855. Is that where this question ends? Right, is the answer choice D here?
No, because it's asking for the solute.
Perfect, right? We do have to solve for the solute. So, right, it's the fraction of the benzoic acid, but we solve for the solvent. So we're just going to take 1 minus 0.88 or 855, excuse me. So this gets 0.145. So this should be C. Does that help with question 6? Great. Okay. And then question 2. Okay. Okay, so for question 2, we have procaine hydrochloride is used as a local anesthetic, and we want to calculate the molarity of a 4.612 molal solution with the density of 1.1066 grams per milliliter, and we're going to assume 1 kilogram of solvent. So the thing to note here is that you're working in between units. Sorry, that was concentration units. That was hard for me to come up with right there. So for molality, we know that molality is moles solute over kilograms solvent. And then we know that molarity is mole solute over liters solution. Okay. So we could find the moles of solute because that's the same between molality and molarity. And we can assume 100 or 1 kilogram of solvent. So we can take 4.612 moles over kilograms is equal to X over 1 kilogram. And if you're super smart, you might see that this is 4.612 moles of the solute. But then the next thing is that we need to get to liters of solution. We are given the density, and the density is for the solution. We already know that we have 1 kilogram of solvent, but we need to find how many grams or kilograms of the solute we have in our system as well. And we can do that by taking the moles of the solute and using our molar mass to get to grams. So we'll take 4.612 moles, use our molar mass, and say that 272.77 grams is equal to 1 mole. And so we get 1,258 grams, which is 1.258 kilograms. Either one that you use is fine. The setup for which part? Sorry, I missed when that came in. Yep, so we have to, right, we know that we have 1 kilogram of solution. I'm sorry, we have 1 kilogram of solvent, and we know the molality. What we don't know is how many moles of our solution we have, right? If we look at our molality breakdown, we need moles of solute, and when we need our molarity breakdown, we have moles of solute. What's given from our question is we don't have moles of solute, but we can solve for that given molality and given the fact that we have 1 kilogram of solvent. So this is just setting up where it's like, okay, we have 4.612 moles of solute over kilograms of solvent equal to whatever this is divided by 1 kilogram. That's where our X comes in. You could also do it where it's 4.612 moles over kilogram, and then you can multiply by 1 kilogram that way, and you get 4.612 moles. And it would be that way. That's the same way. It's just if you want to see it as a proportion or a dimensional analysis. Yep, yeah, so that translates directly, right? We're going to be able to use the 4.612 moles of solute directly for molarity once we find that, because those are the same. Yep. Okay, so then once we have our grams of our solute, in order to get solution, that's going to be 1,258 grams plus 1,000 grams of the solute. So this is solute. This is solvent, right? Because 1 kilogram is 1,000 grams. So we have 2,258 grams solution. And then we can use our density. And if we have 2,258 grams, then for every milliliter, we have 1.1066 grams. So we end up with 2,040 milliliters, which is 2.04 liters of solution. So then we can take the 4.612 moles and the 2.104 liters of solution, and we'll get 4.612 divided by 2.04, and that's equal to molarity, and that should get us 2.260 molar, which would be A. Yes, you should be able to apply that every problem. So if you see like moles of solute or liters of solution anywhere, if you see that across multiple concentration units, then you can apply that. Then you can say like, oh, this is what I have here. You can use that there as well. Molality and molarity are just different ways to show concentration. It depends on like what you're trying to get out of the question. So it's just different ways to represent the same thing. It's just what you need to work with. They're like pretty close. Yeah, I would say they're pretty interchangeable. If you say molarity and you actually mean solubility, people will probably get it. Molarity is the concentration of ions dissolved. So, and that's essentially what solubility is. And you'll find out later in the semester about insoluble salts, and you find out that the solubility is related to the molarity. So they're pretty much the same thing. For purposes right now, they are the same thing. Okay. Any other questions on 2? Does that help? Okay, we'll go to 9. Okay. That will depend on temperature. For the more moles, the greater it is. For solids in a liquid, the greater the temperature, the more things that can get dissolved in it. And then for gases and liquids, then the lower the temperature, the more things that can get dissolved in it. And that's like the fish tank question on your quiz for the gases dissolved in liquids. The solubility of gases will decrease with increasing temperature because you're heating up that solution. So you're expanding more of that, liquid. So the gases aren't going to dissolve as easily because the liquid now looks like more gases. Or it looks more like a gas than it does a liquid. For solids, in liquids, when you heat up the temperature, it allows for that solid to kind of, I would say, like sneak into the pockets almost, if you're thinking visually. And then when it cools back down, it's trapped within those pockets. It eventually will fall out. Right? If you have a super saturated solution, you just push it over the edge, all the extra stuff will fall out. But it has to do with that. Yep. Okay. So for question 9, right, we have an anionic compound MX dissolved in water, and the solution feels cool to the touch. Right, so which of the following pairs of inequalities is correct for this response? So when we say it feels cool to the touch, this is saying that our reaction is endothermic. Okay? The reaction is endothermic. That means that in order to break MX, right, it requires more energy to break the sample than energy released when new solute, solvent, IMFs form. Okay. So that means that in order to take an ionic compound and break it apart into its ions, right, we're breaking a bond in that sense. Ionic compounds transfer electrons, so they have a very strong bond. They both have charges. When we break them apart, that is a bond breakage. All bond breakage requires energy. So you need to put energy into that bond in order to break it. When we then solvate our ions or put them in solution, right, and they dissolve, that releases energy because you're now forming bonds between the solute and then the solvent that surround it, right? We're forming bonds and then or forming IMFs, and all bond formation releases energy. Usually, when a solution forms, right, there's enough of that energy released in order to make it an exothermic reaction, and the process of dissolving the ions releases enough energy and then the solution feels hot. But that doesn't always happen, right? Sometimes it requires more energy to break that bond in the first place than it does once the dissolving actually happens. And in that case, that was what we see here. So since it feels cool, that means that the lattice requires more energy than hydration. If this was the solution feels hot to the touch, then it would be B and C that we're looking for because we're releasing more energy than required to break the lattice. So B and D we can get rid of right now. For the difference between delta H and delta S, in an exothermic reaction, delta S will always be bigger than delta H. Did I say that correctly? I think so. I think it'll always be bigger than that. And then for an endothermic reaction, in order for the solution to form, your delta S has to be bigger than your delta H. So it has to be C for this one because we need to have more entropy to overcome that endothermic reaction that's happening.
Okay, wait, for the lattice, like, I'm like still confused on what the lattice is again. Is the lattice to break the solute? Like, or is the lattice like,
Yes.
wait,
Yep.
I'm like a little confused.
Yep. So the lattice is, right, if we have Na plus and Cl minus, right, what do we know about opposite charges? Do they attract or do they repel?
They attract.
They attract, right? So they have a very strong bond between them. They are like tight. So in order to break that, think about trying to play tug of war and you're trying to separate the middle apart, right? You have to put a lot of energy in order to break those two ends apart. So the lattice is that energy that's held between those atoms. So the energy that that atom and that bond has is the lattice energy. In order to break that lattice, you have to put that same energy into the bond to break it than it does when it's holding that energy together. So delta H of the lattice is what energy you have to put into the molecule in order to separate it into its ions, right? In order to
Okay,
do this,
so for like
and then
that
what?
graph thing that we do in class that has like the upward arrow and then the downward arrow, I don't know if you know what I'm talking about.
Yep. Yeah.
Okay, so is lattice like one of the up arrows?
Yes. Yep. So, right, we like start base level and then we break the ions or we break the lattice and that pushes us up. We had to put energy into our system and do the up arrow in order to get to here, right? Then we needed to break our IMFs in our solute. So that brings us up to here. That's another one of them because we're breaking bonds in all of those. Then we combine them and your down arrow is when they solvate. And when
And
they
that's mixed?
and that's the mix. That's the solution. Yes.
Is that the same as hydration?
Yes.
Okay.
Yep.
For exothermic, would it be like the opposite? Like hydration requires more energy than lattice, and then change in H has to be greater than change in S.
So your delta S will always be greater than your delta H. I think Dr. Altimos put a really good explanation in the group me if you're in that last night about it. And I think your slides also tell you that as well. But in order for a solution to form it, like an exothermic reaction, the solution will always form whether either one of them is the same, but I think delta S is always greater. But in order for an endothermic reaction to form, delta S has to overcome and have to be greater than the delta H of the solution, right? Because we have to put in energy to form solution. So the entropic favorability has to be greater to outweigh that. So
So
sorry, go ahead.
are you saying for either process, entropy has to overcome enthalpy if a solution were to form?
Yes, I believe so.
Okay, thank you.
Yep. So when we look at, right, if we ignore this portion here, this in this portion are for exothermic. And then this one and this one here are for endo. That's what you're looking at for lattice versus hydration. And then if we're looking at the delta H of solution and delta S of solution, then that's when it comes into play of like, is it endo or exothermic? If it's endo, this is the only way that a solution will form. So if it's an endothermic reaction, it always has to be entropy driven. Yes, I believe that is correct in the
Okay,
chat.
thank you so much.
Yep. And then let me just look at those slides real quick so I'm not like feeding you false information. I'll just go find it to make sure that I am saying correct things. So yes, So whenever a solution forms, it is always increasing entropy. It is always increasing entropy, right? A solution by itself and then dissolving things in solution is always increasing entropy. For an exothermic reaction, delta H might, right, that if that's negative, that's favorable by solution or in the universe. Delta S will always be positive. So for an exothermic reaction, sometimes delta H might be bigger than delta S, but it's always favoring solution formation in that case. So the best way to ask this question, number 9 on an exam, is for an endothermic reaction, because if it's an endothermic reaction, delta S must be greater than delta H of solution in order for the solution to form. It would probably tell you in the reaction, or it would tell you in the question saying that, or you could solve for it, or they would tell you that like delta H and delta S are this in that sense. Delta S is always positive. It is always greater than delta H in an endothermic reaction. Does that help clarify some of this stuff? So for an exothermic reaction, one of them might be greater than the other, right? Delta H is not always greater than delta S, and delta S is not always, yeah, that's a great idea. So endo, delta H, all right, we'll say delta S, solution, always greater than delta H solution. And delta H of the lattice is greater than delta H hydration. I feel a sneeze coming. For exo, delta S of the solution and delta H of the solution, both favorable, positive, and negative, right? In this case, delta S will be positive, delta H will be negative. So can't tell which is bigger. But delta H lattice is less than delta H hydration. Yes, someone asked, is this in order for delta G to be spontaneous? And that's like in terms of delta G, and that's correct. Yes. Does that help clarify some of the solution stuff?
Yeah, thank you so much.
Yeah, no problem.
So if it gives us an exothermic reaction, how would we know which inequality to pick if it were to be delta S of solution is bigger or less than delta H of solution?
I don't think you could tell based off of the information given, right? Like if you were given number 9 and for an exothermic reaction, I don't think that there's enough information given for you to answer that question. So there would either need to be more information, or choice E would say need more information. Because both are favorable, so a solution will always form if it's an exothermic reaction.
Thank you.
Yep. They are both technically product favored because the solution forms in both of them. Exothermic is more product favored, I would say. But they are both product favored because solution is forming. and that's increasing entropy. Okay, are there any other questions we want to see?
I wanted to just get like clarification for the last problem. Like I
Yep.
got the number correct. I got like 109, but I put negative because like when I solved for the surroundings, I got a positive answer. So then I assumed like because that's surroundings, then the system has to be negative, but then that doesn't make sense because it's from a liquid to a gas. So like when we get the delta S, do we just assume that's the absolute value and then the sign is for our interpretation?
Yes, I believe so. So when we're looking at, right, when we're looking at the question, it says, what is the entropy change in the system delta S when 1 mole of water vaporizes? Right, we're saying that the system is the reaction happening. So we can use, right, we know that delta G is going to be 0. So solving for delta S, we can assume is for the system because we're using the system's temperature and the system's delta H. So we can just use the delta S directly there. I think that answers your question.
Okay.
Does
Yeah, I think.
that makes right? So like this here is our system. And since it's asking for the delta S of the system, we can use the delta H directly and we don't need to change the sign of it.
Oh, okay.
Right?
Okay, I gotcha.
Your reaction becomes the system here. And then like everything else is your surroundings.
Okay. All right, thank you.
Yep. In terms of absolute value, I think you just need to know that for temperature, right? Like absolute 0 is temperature, and that's when at 0 degrees Kelvin, and that's when no entropy exists, no motion exists, all of that. You just like still nothing. I don't know if that's in the slides for this semester because we probably talked about Kelvin in 119 maybe a little bit. Or no, that would be in the slides. That would be in the entropy slides. Around third law of thermodynamics, I believe. Around that area. Yep. Any other questions? Well, someone asked when the Zoom ends. I'll go for like 15 more minutes, like 8:30, give you an hour. Yeah. So what would I recommend you focus on for the test? So, and then someone asked about 14. I did do this last night, so you can look at my notes right now while I explain the other, what you should focus on. So for your last little bit of prep before the exam, I would say the best thing to focus on is big general topics, right? Look at entropy. Think of all the things you can think about for entropy. Look at delta G. What are the big things that you can think about for delta G, right? If we look at delta G, we know that delta G is spontaneous when it's negative and it's non-spontaneous when it's positive. The world prefers for it to be spontaneous. So how do we get those conditions where delta G is negative, right? That's the big concept there. A lot of the questions after that are just utilizing what's in the equation in order to make delta G negative. If you look at delta G, you know that there's delta H and delta S involved. So then you can say, okay, what is that big thing there? Entropy is disorder. The world prefer disorder. That means that it has to be positive, stuff like that. So just like big general topics that way. Because if you know those general topics, then you can always boil down a question to what's the big question? What's the big topic here? How is it trying to ask me that big question? So, right? Delta G, entropy, and then you have all of your colligative properties. Like, what does it mean, right? The whole thing that we started with, this is solutions. And we're saying what happens when things get dissolved in solution, and what are the consequences of forming a solution, right? So when you form a solution, that means that you're decreasing your vapor pressure. Your pressure of your pure solvent will always be greater than the pressure of your solution. So we're decreasing vapor pressure. We're increasing the boiling point, right? There's more things in solution now that now are competing with the other molecules and forming IMFs that we now need to overcome in order to break that bond to make it into the gaseous phase. And at the same time, we're increasing the boiling point, we're decreasing the freezing point, because again, those IMFs are competing and we need to do more work or need to put in more energy in order to freeze it or boil that compound because of the result of the solution. What else did we talk about? And then it's just like concentration, right? The big topic here is solutions. How do we define a solution? Is it by the moles of the solute? Is it by the liters of the solution? Is it by the kilograms of the solvent, right? Just those big topics there. See if you can kind of think of those big general topics, because at the end of the day, that's what it comes down to. And if you can think, okay, what big general topic is this talking to me about? That might get your brain in a mindset to say, this is how I'm going to answer this question because it's a solutions question, or it's a vapor pressure question, or it's a colligative properties question. So that's what I would kind of do in my last little like read through of questions or something, like what is the big general topic there? Does that help whoever asked that question? Okay. So 14. How do you know something is polar or not? So if you have just carbon hydrogens, right? So the big thing that comes down with polarity is difference in electronegativity. So if you have differing compounds, or differing atoms, you'll have a difference in electronegativity. So since we have a CH3 bonded to an OH, those are different. That's going to be a polar molecule. If we have 4 or more carbons in a chain here, that is what's going to, makes it more nonpolar, because that non-difference in electronegativity is going to outweigh that slightly difference in electronegativity with that OH. I wouldn't recommend reading the chapters for the test right now. I mean, you can skim it, but just to look at vocabulary. But at this point, I think your best bet is to either keep practicing some practice problems, watch these old videos, and if at like the last resort, go back to the textbook to try and look at a little bit more vernacular there. And then for 14, I did do this last night. So if you want a better explanation for like polar, non-polar, just take a look at the video I posted last night. I think it's towards the end. And you can see me explain it last night as well too. Yeah, that's a good way to look at it, Ariana. Yep. Right, so if it has a CH and an OH, that's 1-to-1, we can call that polar. But when we look at like 1-butanol, we have 4 CHs and 1 OH. So it's like 3-to-0, right? So it's going to outweigh and make it nonpolar there. Okay. Yeah, so then freezing point is lower in a solution than compared to pure solvent, because in the same sense that we are looking at boiling point, right, if we're trying to boil a solution, then there are things in solution that are competing when also absorbing that energy, right? There's IMFs between the solution and the solvent that also have to be broken in order to boil that compound. The same thing's happening in the freezing point. It's just instead of breaking those compounds, you're now forming those bonds even more. And so to form those bonds, you need to have more energy and you need to have a little bit lower freezing point because you need to you need to compete with the other things in solution in order to form the bonds and really form, right? You need to move that particle that's a solution out of the way to form the bond with its pure solvent kind of thing, if you think about it that way. Does that help, Jacob? Okay. And then someone asked, is concentration the same as molarity? That is, yes, concentration and molarity are the same. For questions, I would say like your Alex homework are pretty similar, I would say. And then like the end of chapter questions in your textbook. Okay. Okay, so for question 4 here, we need to know that osmotic pressure is IMRT. So we have a 20 molar solution or a 0.2 molar solution of calcium chloride. Calcium chloride is going to dissociate into calcium 2 plus and 2Cl minus. So what is our Van Hoff factor for calcium chloride? Yep, someone said 3. Yep, so this is 3. So I equals 3 for calcium chloride. For iron chloride, right, we're assuming 100% dissociation. This is going to break apart into Fe3 plus and 3Cl minus. So what is your Van Hoff factor for iron chloride? How many ions do we have in solution? Yep, so this is going to be 4. So when we're looking at osmotic pressure, we want these to be the same. So we're just going to set IMRT, and we'll call this one calcium chloride equal to IMRT, and we'll call this one iron chloride. R and T are constants here. They're not changing, so we can get rid of those. And so we're just looking at something where it's 3 times 0.2 equal to 4 times X. And so we get X equal to 0.15, which is D. I think that's how it. Is the answer D? I don't remember. Why do I feel like it's not? No, I was right. Okay, yeah, that's it. Okay, any other questions? So they're slightly different, I believe. I believe there's one slide in your notes. I'm gonna scroll through real quick because I can see it in my head, but I don't know. I can't find it. So right when you're doing a solid and a liquid, Increasing temperature increases solubility, so think of like a supersaturated solution in that case. But in order to dissolve more gases in liquids, then you want to decrease your temperature for that one. So it's inverse. Yep. So then, right, the lower the pressure, the less soluble the gas is. And so if you compress that and make it higher pressure, then you get more gas bubbles dissolved. Yep. Yes. Yep. Yep. Lower the pressure, the less soluble the gas. You had it correct in your first one. So you're just like compressing the gas down in your liquid. So think that you're like shoving the gas particles into the liquid more, right? It's more pressure, it has to tighten up in order to fit those gas bubbles in there. So it creates more solubility, right? It needs to take up less space, so it goes into solution. I don't think they would ask that kind of question. We're just looking at solubility. I don't think you really, I don't know what that entropy change would be, but I don't think I've seen any questions where you're gonna talk about solubility and then the entropy. Sorry. Okay, any other questions? Are we feeling okay? Get a good night's rest. Get some sleep. Make sure you eat before your exam. Set multiple alarms if this. I don't know why my AirPods keep on connecting. Okay, I guess we'll call it a day then. Good luck tomorrow. And let me know if you have any questions. You can always send me an email. That is totally fine. I'll get back to it hopefully before the exam. Okay, thanks y'all. Good night. Thank you for coming. Have a great night. Good luck. If I don't see you before the exam. Bye-bye.